excited, and I'd like to present some work on our killing skills, our shooting skills. And to illustrate this presentation, I will start with a nice video. And this video is a game against us against Gambada, and we make such a beautiful goal. However, seeing this goal, we were as surprised as everybody else there that we could make this goal. So therefore, I want to present you today our work on repeating such goals. So first, I go more into detail in our shooting mechanism. So what's the system about, design of the actuator. Then I will continue about our lob shots. First, we have to identify a system and then calibrate it. And then I will tell a little bit about our work towards controlled shooting. So first, I'll tell you the problems we have to, and then some proposed implementation. So, the shooting mechanism. Before we can design, we need to have some requirement specifications. So we want to have a controllable shooter, which can shoot hard, soft, can shoot a lob shot or just a flat, and of course, very important, repeatable. Now, as these are rather vague terms, I'll come into these back more later in this presentation, but we also have some hard specifications, such as we want to have an end speed of 9 meters per second of the actuator. We have moving of the moving part is 90 millimeters. Then it should all happen in about 20 milliseconds. And we are wishing to, want to approximately have 450 meters per second squared acceleration. So the system. The shooting system is built up from our robot battery. We convert that to about 350 volts into a capacitor, and this capacitor, by using an IGBT and a PWM modulation, we excite the actuator, which then has a lever and a pin on it, and it will shoot the ball away. Now for this moment we go more into detail in the actuator design. The actuator design has a mechanical design, so it has a stator and it has a moving part. This moving part will move in this direction. Looking at this design electromagnetically, we can see as a soft magnetic part is the back, a magnetic part of the plunger, and a non-magnetic part of the plunger. By exciting the coils, we create a magnetic field which will attract the soft magnetic part, and therefore it will shoot, it will go in this direction. So in this design we had to investigate several aspects, such as saturation, eddy currents, losses, and thermal issues. First we looked into saturation. So how much current can we excite before we get into saturation? On this picture you can see we designed the actuator in such a way that we reach the top of the linear part of the saturation curve. So we get the best losses, current, and force ratio. As you can see, it's nice, about 2.4 Tesla here, and in the back of the stator it stays nice unsaturated for 1.5 Tesla. Then we have the final design, which came at a 4.5 kilogram mass, total mass. We have a peak force of 700 Newton, and the peak current is 110 amps. So we generate 700 Newton meters by exciting 110 amps in just 20 milliseconds. So how does it look like? So this is the final design, and we have here the block inside the turtle, and it actuates this lever and the pin, and then it will shoot the ball. You can see the pin here. And I will show you a short slow motion movie shooting at full power, shooting a lob shot at full power. As you can, you have to wait. In this movie, you really see the power which comes freely, because the pin really goes into the ball. So there's a lot of power that comes free. Well, now we have such a power, but we also need to know how to use such force. So therefore, we want to use for lob shots. Now for lob shots, the idea for the lob shot is to shoot between the keeper and the goal crossbar. And to do that, we want to have a trajectory that has the largest gradient right at this point. So basically, it goes, it has the maximum height here. Applying to this constraint, we have a lob shot. Well, we first need to know what kind of relation between the duty cycle of the system and the distance we can shoot. Well, we identified that it should be an exponential function. So we have a duty cycle and we have a distance, which depends on three different parameters, which is C, A, and B. But from our test, it appeared that each actuator has its own characteristics. So therefore, we have to calibrate each turtle individually to find out what these three parameters are. So doing this, as this, we need three parameters, so therefore we need at least three measurements. How do we do it? Well, we just take a duty cycle, we choose a distance, we take a duty cycle, we let it shoot, and from there we can measure the distance. So you really just measure with a ball game from the distance to the turtle. And from this we can identify the parameters, the unknown parameters. Well, on the tournament we want to do this as fast as possible, so we have more time for development. So therefore we developed a calibration GUI. In this calibration GUI we can select the turtle, we have some input, which we can place the points and then just say make a fit, and it calculates the unknown parameters. It just copies these parameters to the turtle and we have calibrated. So at this point we can shoot, we can make a lob shot and we will know at which distance the ball comes, will end. However, to make the perfect lob, we want to shoot just beneath the crossbar. So the distance from the ball to the point the ball needs to land depends on the distance between the ball and the distance between the ball and the goal. So this length we still need to tune. And that we do because we know the distance to this point, we know the field, we know where the turtle is, we know where the ball is. So for this correction, we can calculate this correction by a linear approximation. Now we know how to, well, now we have lob shots. However, it's still a lot of work to calibrate for each turtle. Because there's still some variation, so it makes also the tuning difficult. Furthermore, we have a relation between the kick-up and the outfall is not linear, so this again another layer of complexity. The current system is open loop, so it's just a feed forward. Hopefully, we only can hope the calibration is correctly. And it is especially time consuming. So what do we want? Well, we want a more predictable behavior. So which will decrease the tuning effort, so more linear behavior, and we want to decrease the variation between the turtles. So when we shoot, when the turtle had to shoot, it should exactly land where we predicted that it should be landing. So the proposed implementation is that we have an encoder on top of the lever. This encoder will say its position of the lever, the angle of the lever, which is attached to the plunger, and when it will shoot the ball away. So what we propose is that we have a control algorithm that controls the PWM signal that will be sent to the amplifier. Then the encoder gives feedback, and we can again adjust the PWM signal. The control algorithm looks a little bit like this. So we have a speed set point. It goes feed forward in, And then we have a closed loop, which keeps on correcting the speed so that the ball has a linear output speed. We have already some similar. So the idea of the is that instead of just shooting at maximum power, we shoot more. We first set the pin against the ball and more guide the ball, like curling, to its end velocity. However, of course, it will never be exactly like curling because it's a ball and we want to have a reasonable output speed. So therefore, it will be somewhere in between. Further, we have to consider some limitations because the encoder resolution has some limitations. So when shooting at full power, we cannot control it anymore because it just goes too fast. Furthermore, we cannot brake, so we really have to think before exciting the current if it will not be too much. And furthermore, as I told, the idea is to guide the ball instead of fully shoot at it. So the current, our simulation results and the current situation is as follows. So this is the position of the blue line is the lever and the green line is the ball position. So as first the lever goes to the ball, then the pin goes in the ball as you saw in the slow motion video, and then at this point the ball will fly away. And then you can see that the lever will also accelerate, however will not touch the ball anymore, and this is the end point of the pin.
How do you define the ball position? Because the ball is not round anymore and the pin is inside.
These are just simulations. What we did is model the ball, so it has some deformation, and knowing its properties, you can model the ball rather accurately.
So here the ball position is basically the center of the ball.
Yeah. Looking at this picture only for speed, you can see that the lever will increase in speed until the point you will touch the ball. Then the energy of the lever goes into the ball, and at this point the deformation of the ball will bounce off of the lever, so it gives a negative force to the lever, and then you see that the ball has this output speed, and the lever again goes to the final position, and then you see that it will end. Well, what we propose on this control is to really guide the ball. As you can see, we first bring the lever position to the ball. At this point, the pin is touching the ball, and from this point we guide, keeping the position the same of the lever and the ball. Then we have again the speed picture. So this piece is positioning the lever against the ball, and here you see some curling, and that's mainly the interaction of the lever with the ball. And you can see you can here really arrange us having a linear output speed. And these results give us a more reliable prediction where the ball will be in the next seconds. This brings me to the summary and conclusion. So we have designed and optimized a shooting mechanism which we now use in the turtles. We identified an exponential relation between the duty cycles and the kicking distance for lob shots. We can calibrate these lob shots while using a graphical user interface. Furthermore, we have a feedback control design for to control the output speed of the ball. And we modeled and simulated this feedback control of the shooting mechanism. Therefore, I want to thank you for your attention.
One of the questions I have, you talked at the beginning of the talk, you said something about repeatability. Yes. Okay. Do you experience some kind of magnetization of the plunger, for instance, if you shoot several times in a short period? Because that will change the behavior of the...
Yeah, normally it's more or less this reasons effect, I guess, from the metal. But I must say we don't really have experience changes because of that. And I guess the reason is because the amount of magnetization we put into it, so we really go to 2.5 Tesla. So the resting magnetization that is in it, I guess it's almost negligible.
If you want to guide the ball more, can't you go from a pin to more
That's an excellent question, because we have also some internal discussion about this issue. At this point we don't know exactly yet, but we are testing by, instead of a pin guiding, having a surface that exactly fits the ball, so we can control the aim. However, the difference is we chose past the pin because we have more output force, so we can shoot harder. However, now we know
power is transmitted from the lever to the ball mechanically, irrespective of the contact surface. Huh? I'm making a mechanical mistake there. It's a transmission power from triangle system.
Yeah, but
no? There are all kinds of losses, as far as I understood it. I don't know how much percentage of the power you put into actually. Yeah, but the more you deform the ball, the higher the losses are going to be. They will maybe the way of deforming is determines how much loss you have. So the least deformation and the less loss of power. Huh?
yeah,
That's too simplistic reasoning.
but if you have a pin, you have more elastic power from the ball. Because you have more deformation in the ball, it lasts more.
You tension a spring that is later decompressed. You don't have to tension a spring.
Maybe even more time.
Because actually you did decelerate.
I find this.
There might also be more time with contact between ball and leather. So maybe you could, the energy over time is higher than, I don't know, just a guess.
Simple mechanics, you have the losses and the deformation, that's all.
Well, from early tests, but maybe there are two.
Also, real soccer players don't kick with their tips.
But that is accurate.
It's at one moment.
It's like accurate.
They still kick the ball, they don't push it, so they still deform it while kicking. The main thing is also that the time you actually have to hit the ball is a very restricted area to hit it and very restricted time. Maybe you don't have the time to actually push it. We did some quick and dirty tests with instead of a pin, have a hitting surface, just compressing the ball. And what we found out so far is that it does not have more power. And it's probably due to losses or, not to see.
But yeah, barely you lose. So that's
It's interesting indeed because
But that's an interesting question because, for instance, in our previous version of the robot, we actually drive the ball instead of kicking it because the design of the kicker it didn't have the pin itself, so we actually involve the ball and drive it. And now we have a pin, and it's much better in terms of the power you can have on the ball. I can assure that for practical reasons. From theoretical point of view, I agree with you. So probably there are other things involved in it.
because on your figure it looks like the contacts with the ball is already gone halfway to the motion of the lens.
This picture, I guess.
Yeah.
But
So after 0.125 or so, the ball is
but these are simulations, but when we model the ball, we get these results.
Yeah, that's another question because, of course, the ball, the real ball, is completely different depending on the it is.
Yeah, exactly. Yeah, of course.
You have sewing, so depending on the point you hit, you have a different result. And something you have to live with.
Yeah, some deviation.
Yeah, but these differences are also more distinct to the opinion of the surface.
Yeah, you're right about
Surface,
that. Yes, you're right about that. Yes.
So are you using that calibration in the game? Is that
During the game.
to shoot, to kick the ball?
For the lock calibration, you mean?
Yes.
Yeah.
Yes.
So no, that's before the game. So you do it before when you start the
Okay,
turn.
you calibrate before you use those parameters
In
when
the
you want to kick in the game.
Yeah, for lob shots.
Okay.
At this point, only for the lob shots. The flat shots, well, you don't. Yeah, the distance is. Yeah. You could
Do you do any correction with the robot, the velocity?
Yeah. You also encounter rocket velocity. You can tune it also. And we're also planning to include correction for the voltage of the capacitor. Because when you shoot twice, it's a short time, so it needs about 18 seconds to load. If you shoot within these 18 seconds. 18, yeah.
After shot, full power.
Yeah, full power. 18 seconds.
Yeah, that's too long.
You always go for the good shots. Make a goal.
But I want to note, it doesn't require 18 seconds to shoot again. It will not be at full power, but
Of course, to have full power again.
yeah.
Okay, and what is the error you have? Oh, I mean, in the same distance, you want to shoot the same power. What is the error you are having?
10 centimeters, 20 centimeters.
I was asking because we did similar work and similar research 2 years ago, I think. And we actually came to a function that we would input the distance, we would input the height of the ball where we want to have the ball pass in that distance. And at the end of the day it worked well, and in the other day in the morning it was completely off.
Okay, that's
Like when or 20 centimeters.
Yeah, but I think that this has to do with magnetization. Yeah.
But I was thinking,
Of the blender.
because you magnetize it each time the same way, so at a certain point,
Yeah, but if you wait 20 hours or so,
oh,
it
you
loses magnetization effect. So what we started doing for making I don't know, 10 or 20 shots before a game, so that we reach magnetization level that we had when we had breakthrough shots.
that's a good idea, because we also want to go a little bit that way, but maybe we can discuss more.
And you know how to defend.
Yeah.
What kind of sensor do you use to determine the angle of the shuttle? Because there was there's an encoder, and this is, how is it
It gives a position.
How is it exactly done?
It's an optical encoder. It's an incremental disk.
Oh, okay. So what's the speed of? I wonder, because most sensors are not fast enough to somehow use it for your application. So this is
So
why
I
I
use the exact same sensors on the drive motors, and we just send them 1,000 words, and we can also.
Okay.
But again, the idea for this is also for, at this point, for passes. So at passes we don't want to shoot at maximum power, so it's about 50% of our power we can shoot at maximum for this idea.
Now you have a good model for how you can shoot, what your output will be, and you can calibrate it per robot. But now you get in the field and you have an unknown ball. How do you handle that?
Well, the controller should, because then you create an error, and the controller should solve that problem. because indeed the identification with the lob shots, you have that problem. So you really need to check before you go in the end game that the ball should have the right pressure. And it's also a problem with this method.
Yeah.
It's,
1.6.
Yes. There are official balls, which means that they know which are the balls they're going to play with. And there's the guy that always checks the pressure of the ball. So that's the setup.
And things like the shape of the ball or so, the details are not of influence.
Yes.
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 It's a visual feedback ball.
Okay, so that's also a problem.
Yeah.
But indeed, it is a good remark. Indeed, because the ball is not perfectly round, you have also where you, the air push the air in the ball, or you have the how far you can take the ball with you with the ball handling system. These are all factors, and it indeed makes the system rather unstable.
It's always complex.
So, therefore we also use the tuning. So we can tune and say, well, okay, we want to tune it like it's such that the 80% of all balls will be in the goal, and some other percentage will better. That's also in real life, I guess, for footballs. You know, it's also sometimes missed. Yeah, also?
Did you make also any experience with using coils also on the plumber? So you have not these problems with magnetic?
So basically what you do is an induction motor.
Yeah, something like this, so if you don't have a permanent magnetic field?
I must fairly say I'm not, well, I don't know the problems that arise. However, I know that one of my colleagues looked at it in the past, and from all the different topologies, he chose to choose the reluctance actuator because it has the best performance as we could judge then. I'm not aware why, but it could be an active. Any other questions?
Maybe you can go into the second slide with your speed simulation.
Okay.
Yes, to the settings of this. I think the speed is just the derivation of the position, but there are kind of steps in your function with the speed.
Yes.
Yes. Where do they come from? So speed.
This is the interaction between the ball and the lever. So when the lever pushes, the ball deformates and again becomes the ball again.
Ah, okay.
That's what you see in this.
You're always trying to get the maximum slope when the ball enters the goal.
Yeah.
But would it be better to have a lower slope and to maximize the uncertainty that you can get in your shot and you still score a goal? Can have a lower shot, a lower lob?
So you mean that you have more chance to be in the goal instead of?
So even if your shot doesn't come as you would want, it will still score.
Yeah, but still have a goalkeeper in front.
Yeah, that's the problem. You want to be preferable vertical, just beneath the goalkeeper.
Just need to do it above it. So if the ball keeps above it for a long time, and within that region where it enters the goal, it's very nice. You see, because if you are getting the maximum slope, the amount of time that the ball will enter the goal is quite small. If you have a lower lob, the ball will be in that 8 for a longer period.
Yeah, it's just something you can do.
Yeah, the question is the movie you showed like, with the goal against Nevada, how a goalkeeper doesn't have the moving arm
be in this region,
Yes,
so
That's it.
yeah, you want to shoot or
If you
exactly
shoot
straight
or
here.
If you straight, it will be stuck between the.
Yeah.
Because
Yeah.
the hole is slightly, the diameter is slightly larger than the 20 centimeters you have there.
Oude sombrero.
Yeah. Okay.
Any other questions?
Okay. Thanks so much.
Thank you.